Let's talk about the continuity of a function. The function f of x is continuous at a point c, comma f of c, if and only if all of the following are true. The limit of f of x as x approaches c exists, the actual value of f of c exists, and they happen to be the same. What does it mean to have a continuous function? In basic terms, a function is continuous as long as you can draw it entirely without picking up your pen. Continuity on a closed interval. A function f is continuous on a closed interval if it is continuous on the open interval ab. Okay, so closed interval, see the brackets means a closed interval. It includes a, it includes b. And this one is our open interval. Everything to a, everything to b, but not including them. If it is continuous on the open interval a, b, remember, open interval not including a or b. And the limit of f of x as x approaches a from the right is the same as f of a. Okay, it must be the actual valuation. The limit of f of x as we approach b from the left must be f of b. Then we can say the function is continuous from the right at a and continuous from the left at b. Let's imagine we have a graph. This is some interval. This is going to be a, and this is going to be b. So this is our interval. Must be continuous on the open interval a, b. The limit as x approaches a from the right must be f of a. Okay, so as we're approaching a from the right, the limit must be f of a. All right. The limit as x approaches b from the left must be equal to f of b. Okay, that gives us continuity on a closed interval. The types of discontinuity are here. You have point discontinuity, which takes place literally at just one point. It's like a point from the function has been plucked out and put somewhere else. The limit exists, the value of f of 0 exists, but they're not the same, okay? And that is the definition of continuity. The limit needs to exist, the value needs to exist, and they have to be the same. Removable discontinuity. All I would have to do is put a little point in this hole and it would be a continuous function. But there's a hole there, so it's called removable because one point would remove its discontinuity and make it continuous. As you can see here, the limit exists, but the value of f of 0 does not. Here we have jump discontinuity. The limit does not exist. The value in this case does not exist either. There's a complete disconnect. Infinite discontinuity, okay, usually refers to a vertical asymptote of some kind where you're going either up to infinity or down to negative infinity. Either way, it's not continuous because something's in the way. And in that case, the limit does not exist. Oscillation takes place when the function is just jumping between several values and basically can't make up its mind where it wants to go, and in that case, the limit does not exist. Let's discuss the continuity of f of x. You may not immediately know what this looks like, but you do know you can't take the square root of a negative, so let's just test out some things in our domain, see if they work out. Negative 2 would be 1 minus 4. Negative 3, square root. That doesn't exist. That's undefined. We're going to graph these points. I kind of wanted to know what happens in between, so I decided to plug in like 1/2, and this is what I got. The square root of 1 minus 1/2 squared, which is the square root of 1 minus 1/4. Square root 3/4 equals square root 3 over 2. And I thought that was a very familiar value, that at 1/2 we would go up root 3 over 2. I was like, wait a minute, that sounds like the unit circle. And indeed, this function right here is just half of the unit circle. Remember, algebraically, the unit circle is x squared plus y squared equals 1. But if we ended up solving for y, we would subtract x squared on both sides and then square root, and we would end up with the function that we have here in number 1. Okay, we see the continuity from the graph. Let's check from the definition if this is truly continuous on the closed interval -1 to 1. It is if it's continuous on the open interval and if these limits are what they say they are. So I'm going to plug in our values. A is going to be -1 and B will be +1. This is the interval based on the x-axis numbers. I've plugged in -1 and 1 for our A and our B, and now we're testing to see, are these truly equivalent? If they are, then we gave the appropriate closed interval. The limit as you approach -1 from the right is clearly 0, and as we approach B from the left, that is also 0. And f of -1 is 0, f of 1 is 0, therefore we were correct, as we saw graphically, it's continuous on the interval -1 to 1. There are ways we can test for continuity. There are properties of continuity, such as if f is a continuous function, then timesing it by some constant is not going to make it not continuous. Okay, so scalar multiples, sum and difference, product, and quotient, and then you have composite functions. If g is continuous at c and f is continuous at g of c, then f of g of x is continuous at c, f of g of x. Another way that they write that is this. So both these mean the exact same thing. It's putting one function inside of the other function for the variable. Are the following functions continuous at every point in their domain? This is the sum of, you have the function y equals x, and then you have the function y2 equals sine x, and then what f of x is a sum of those functions, is y1 plus y2. All right. This is a linear function, so it's continuous at every point. Sine is also continuous at every point. So, is this function continuous at every point in its domain? Yes. Here we have the constant 3 being multiplied by our function, tangent x. So g of x is really just taking, fuck me, I shouldn't say that. Here we have the function tangent x. Here we have the function tangent x, and it's being multiplied by a constant. So, is tangent x a continuous function? No. Tangent x has a lot of vertical asymptotes. So this is not a continuous function. Is 3 tangent x continuous? This is just the function tangent x being multiplied by the scalar 3. Now you may say tangent x is not a continuous function, for there are many vertical asymptotes. But the question is asking, are the following functions continuous at every point in their domain? Tangent is continuous at every point in its domain. The points at which it is not continuous are not in its domain. They are vertical asymptotes. So yes, this is continuous at every point in its domain. The vertical asymptotes are not in the domain. So therefore, they do not make this not a continuous function for every point in its domain. Whew. Now if I just said, is the function continuous? No. Moving on. We have a quotient of functions. So you have the polynomial x squared plus 1, and then you have the denominator is cosine x. Polynomials are continuous functions, and cosine x is a continuous function for every point in its domain and entirely continuous. Therefore, the quotient of these functions is also continuous for every point in its domain. Here we have a composite function. You're taking sine of 3 of x. So the outside function, I'm going to just use f and g and put f as the outside function and g as the inside. I hope that's not confusing because it's technically labeled f of x. F of x we'll call sine of x, and then the inside function g of x is what you're taking the sine of, which is 3x. Sine x is a continuous function for every point in its domain. This is linear, so that's continuous, meaning the composite of these two functions is also continuous at every point in its domain. Another composite, we have the outside function is square root x. And g of x, what you're putting under the square root is the polynomial x squared plus 1. Square root x, that's a continuous function for every point in its domain. X squared plus 1, that's also continuous. Therefore, the composite of these is continuous as well. Your outside function is tangent of x. Your inside function is the rational 1 over x. 1 over x has a vertical asymptote. Tangent also has a vertical asymptote. But anytime they don't have asymptotes, they are continuous. There aren't jumps, there aren't kinks, there aren't other things, holes going on. Okay, for the simple tangent x and 1 over x, they are continuous functions for every point that's in their domain. Therefore, the composite of those functions is also continuous. Describe the intervals on which each function is continuous. We know tangent x is continuous for every point on its domain. However, its vertical asymptotes, which are points that are not in its domain, are discontinuities that we need to take into account. All right, tangent x, your first discontinuity or vertical asymptote lies at pi halves. And the period of tangent is pi, so every time we add pi or subtract pi, we are finding another asymptote. So your vertical asymptotes happen at pi halves plus pin, because there are an infinite amount of vertical asymptotes. There's an infinite amount of intervals for continuity, so I'm just going to show a few of them. Starting at -3 pi halves. Remember, each interval is pi in width. So -3 pi halves plus pi would be -pi halves. Our next interval is -pi halves up to pi halves. Continuing on, pi halves up to 3 pi halves. That goes on forever, right? So the intervals of continuity, I've shown 3 of them here, and the ... dots that show that it continues on. Describe the intervals on which this function is continuous. Sine of 1 over x only does not exist when x is equal to 0. And then they say that at 0, y is equal to 0. So my only discontinuity is at 0. All the way from -infinity up to 0 and 0 to +infinity are the intervals of continuity for this function. Now we have x times sine 1 over x. X cannot equal 0. Continuity to help us out with this one. So first I'm going to look for the limit as x approaches a of h of x. Here we are using 0 as a because I want to know if the limit of the function approaches 0 and the value of the function is 0, then it is a continuous function. How do I find the limit of x sine 1 over x? I'm going to use the squeeze theorem. If a function is between 2 other functions, then its limit is between the limits of the 2 other functions. If the limits of the 2 other functions are the same, then the limit of the middle function is that as well. So the limit as x approaches 0 of h of x, the function sine 1 over x is between -1 and 1. Sine of anything is between -1 and 1. Now I need this to be x times sine of 1 over x. So I'm going to multiply everything by x to get -x is less than or equal to x sine of 1 over x less than or equal to x. The limit as x approaches 0 of -x is less than or equal to the limit of the middle function, which is what we started off to find. X times sine 1 over x is less than or equal to the limit as x approaches 0 of x. We use direct substitution since -x and x are both polynomials, they are linear. And so this would be 0 is less than or equal to the limit as x approaches 0 of x sine of 1 over x, and is less than or equal to 0. Therefore, the limit of h of x as x approaches 0 is 0. The piecewise function also gave us the value at 0, which is 0. So if the limit at a is equal to the value at a, h of 0 is also equal to 0, then this is a continuous function. This is a continuous function for all real numbers. Or you can say negative infinity to infinity as well.
And graphically, you can see that this does line up with our intervals of continuity.
And that is testing for continuity.